So,
Dr. Cohen, do you have our hand copies? Do you have them all graded?
yeah, oh, sorry, I keep forgetting to bring them in. They're on my desk at home. So, yeah, I'll try to bring them in this week.
Can you just bring them in your office? We can see them.
Yeah, I'm working on it. Yeah.
Into the bag.
So, last week remember we were going through 3 different performance facets, I guess. And when we design a control system, we have to make sure that it performs correctly, or at least performs well by some standards. So that's what we're developing. Before we start to design control systems, which is what we're going to start doing very, very soon, hopefully next week. Well, maybe not quite. We'll start to lay a little bit more foundation next week, but in a couple weeks we'll be designing them. And we're going to need to know what we're trying to get out of it, right? So you can design a control system and a controller and put it in there. Something happens. We want to have some sort of idea if that's a good thing or not. What happens when you put your controller in there. And also, we don't want it to be a complete guess and check situation. We want to be guided by some performance criteria. So this is sort of the topic that we've been talking about. What is the performance of a control system? Last chapter was pretty straightforward. It's talking about stability. We needed to have a stable system. When we put the controller in there, it should at least be stable. That was our main goal. So in this chapter, it's about transient response performance. We're going to develop some specific criteria for, or I guess metrics for the response of a system, the transient response of a system. And these will help guide our designs later on. So, stable system time responses are often described in terms of 2 intervals, loosely defined as transient, the first part during which the effects of the initial conditions remain significant, and steady state, the second part during which the response has settled near its final value or final amplitude of oscillation. So these are familiar concepts for us, right? Transient and steady state response. We've talked about them quite a bit in the past. So we're going to focus on transient for now. In this chapter, we consider performance in terms of transient response. In the next, we'll consider it in terms of the steady state response, specifically as steady state error. So we'll get to steady state next chapter. And then, in fact, next chapter is going to be Wednesday. So we're going to move through these 2 chapters this week. Transient response characteristics are typically found via 2 methods. Actually, Friday. Wednesday, I got a little bit more, chapter 3. So transient response characteristics are found via 2 methods. Analytically and precisely. So when you do it analytically, you can either have it be precisely for first and second order systems without zeros. So we'll develop those analytically completely all the way through for systems that are first and second order without zeros, which only they make up a portion of systems that we'll encounter, but there's a lot that don't fit into that category, right? And then the other option is analytically approximately for first and second order systems with zeros and higher order systems that have dominant poles relatively close to the imaginary complex plane axis. So this is the analytically side, and then numerically in simulation. So in the lectures today, lecture today and lecture on Wednesday, we're going to explore 1 and 2. On Wednesday, we'll do some numerical stuff. We'll do some simulation. But at first, we'll focus on analytic response characteristics. The analytical method is especially advantageous for design. Design methods, we will learn in Chapter 6, require we place the closed loop poles in the complex plane. Okay? The transient response depends very much on this placement, and exactly how is something we can better understand from studying first and second order system response. We can only simulate systems defined by concrete numbers, so simulation, although powerful, it's typically more helpful to fine-tune a controller rather than design it from scratch. So the analytical stuff, you might say, oh, well, we can only do that for really simple systems. But it's still our guide even for more complex systems. We approximate the higher order systems as first and second order systems, in part because it's relatively true in a lot of cases. It's pretty accurate, but in part because it gives us some way to start our design. Even if it's a bad assumption, which sometimes it is. Sometimes it's a bad assumption to say, oh, this is like a second order system, but it's fourth order, and it doesn't meet the criteria for a good approximation of second order system. We'll still treat it like second order because it gives us a place to start with our design. And then we'll have to always simulate at the end and tweak to get it to fit into the performance criteria that we have for it. So that's the sort of like, there's these two aspects. There's the analytic side where things are supposed to be nice and clean and exact, and then there's this numerical side, which is not. We use both. And we're going to kind of go back and forth. And this is when you guys are, I think you guys are in machine design right now, right? Most of you? So you guys are getting some exposure to the design process, which is very non-linear, right? Like you'll try this, even in those like designing like the diameter of a shaft for fatigue. Are you guys doing fatigue yet? Yeah. So like with that one, you have to iterate on it, right? Like you guess something and you try it, and then you have to like go back and try another one that's gets closer. Like that iterative process, that is really common in design. You have to try something, tweak it, see what would happen, and it's not a completely straightforward process. So it's not just simply, oh, we have to like revise our design and stuff like that. It's a matter of even how do you determine where to start. It can be kind of hard. So sort of bootstrapping off of simple models is really common. Okay, that's what we're going to do. All right, good. So let's actually just go right into 3.1 because that was just the intro to chapter 3. So we're going to define in this lecture transient response characteristics in general. So this is like really sort of high-level definitions. We define 4 transient response characteristics, all defined in terms of a system's step input response. So step responses are the way that we typically characterize the transient response. So think about what a step response is. You take the input to the system and you suddenly, I mean in an instant, you change the input from one value to another value, from 0 to 1 for a unit step. So the step response is how the system responds to that sudden step change in its input. And so it characterizes the transient response pretty well. Like you could do a Dirac delta, impulse, which would, characterize it. Even a ramp function would characterize it. But we're going to use a step because that's the standard sort of way that people do this. They always use the step. It's pretty good, and you guys will kind of see why. Step response is really indicative of how a system's going to respond to an input in the transient way. So, for the following, please refer to the illustration of figure 3.1. So this figure is going to illustrate all of the different response characteristics we're going to describe or define now. So the first one we'll define is the rise time, TR. It's the duration from the time the response reaches 10% to the time it reaches 90% of its final value. So on the graph, so we have a step response here for what looks to be something like a second order system, right? Some overshoot and some damped oscillation. The rise time is the time it takes to go from 10%, so this is when it gets to 10% of its final value right here, so the time at which that happens. And then the time at which it gets to 90% of its final value. So this time interval is the rise time. So it indicates sort of how much time it takes for the system to respond to a sudden change in the input. Okay, so that's one of our characteristics. The next is the peak time. So the peak time is the time at which the response reaches its first or maximum peak. So that would be this peak here, and that time is called the peak time. Now, this definition and I think the last definition assume that we're using the start of the or the start of the step input at time 0. So otherwise, it's the time interval from start to TP. But if we just say that it starts at time 0, we can just say the time TP. It's the time it takes to get to the peak. So it's that. Technically, it's an interval, but usually we take the initial time to be 0, so we can just read the time off the axis, and that is equal to the interval. Okay, and then the last two I would say are the most commonly used. Okay, so 3, the percent overshoot. This one's really an important one. Percent overshoot expresses the amount the response overshoots a steady state value, expressed as a percentage of the steady state value. So the percent overshoot is this peak value, this y peak value, minus the steady state value. So the steady state value here is that, right? So minus that, so this interval here, divided by y steady state. So it's saying how much did it overshoot, by what percentage did it overshoot its final value? And it's always expressed as a percent. So percent overshoot. So if you have a percent overshoot of 10, it's not 1,000%, it's 10%. All right, good. The settling time, TS, is the time at which the response reaches and thereafter remains within plus or minus 2% of its steady state value. So you notice this, well, you guys can't see it on the screen, but on your note sheet you should see it. There's a band that I drew on here, light gray band, that goes plus or minus 2% from the steady state value. So we're looking for the time at which it enters that band and never leaves it again. So it enters that band here, but it leaves it again. It enters that band here, but it leaves it again. Enters the band here, but it leaves it again. Enters it finally here, and it doesn't leave it again. This apparently, it's hard to tell from the graph, but apparently it doesn't leave it here. This is not leaving it, so this is the settling time here. So these last two are really important. So the percent overshoot and the settling time. Settling time is how long does it take it to adjust to this new value, okay? And the percent overshoot is it depends on the system. Sometimes we care about percent overshoot. It's very much related to the damping. But percent overshoot is a really important performance measure, especially if you're dealing with something that has maybe would be, I guess, it would be bad for it to go over its final value. So for instance, say you're going to change the pressure in some a pressure vessel, and you're going to suddenly change it from like this value to this other value. Like that's the set. The set pressure is here, and then you want to change it to set pressure, this other set pressure. And you're going to like the max pressure that it should be set at, and so you don't want it to go over that value ever, right? So if your control system in closed loop with the physical system overshoots that final value by like 20%, like 20% overshoot, that would be really bad, right? So with your controller design, you would want to make sure that your percent overshoot was maybe 0. Like you wouldn't want to have any overshoot. it would want to behave as an overdamped system. Yeah.
What are the units on the y-axis?
So this, it depends on what your output is. So I didn't put units here. This is time. I should have said that explicitly. This is whatever your output is. So it could be meters if you're controlling the position of something. It could be voltage if you're controlling the voltage of something. It could be pressure if it's the pressure of something. So your control system is what you're trying to control is what the output is doing, right? So this output, we want to make it do something, and say we suddenly changed what we wanted to make it do. So the command suddenly changed from, say, you want it to be at 0 pressure to be at like 100 psi, something pedestrian. This would be how the system responds to that sudden change in the command.
So if you were like, that was like voltage or whatever else, something high energy, and your percent overshoot was extreme high, you could probably blow up your system, correct, before you got back to steady?
Right, so this is, if you had a high percent overshoot, that could be a big problem, right? So depending on your system, maybe you care about it. Maybe another system, you don't care. So for instance, there are, I think that the elevator designers have changed their method over the years. They used to apparently not care about a little bit of overshoot. Have you guys ever stopped in an old elevator and have it go like that? It's not very comfortable. Eventually they were like, no, people don't like that. So they did away with that as like, but it's faster is the reason why they would do it, is it's faster to have a little bit of overshoot to get it to stop at a new position. Yeah, people don't like it though. So they slowly approach it now and stop. They go fast and then they slow down and they stop. So there's no overshoot now in an elevator commanded position, whereas there used to be a little bit of overshoot. So there are some cases where like you can deal with a little bit, others you can't. Say you're positioning a robot arm from like this position to that position. The little bit of overshoot might not be a big deal in that case. Maybe you care about it being fast instead of having a little bit of overshoot. Might not be a big deal instead, but it might be. I mean, maybe you're doing robot surgery, in which case probably don't want that overshoot. At least not on me. No, thank you. Okay. Yeah. So these are the different. So these 4 different definitions. Notice they don't depend on like the order of the system. They don't depend on. I mean, some of them aren't defined for a system that is, say, a system that never has a peak isn't going to have a peak time, and it's not going to have a percent overshoot. It's 0, right? It's just non-existent. So there are certain cases where they won't be defined or will just be 0 for a system. But this doesn't depend on it being a first-order system, a second-order system, a fourth-order system. All these systems can be characterized with these definitions, okay? And that's important. So even when we have like a fourth-order system in our control system, we can test for these even when we don't have an analytic description of it. And we'll test for them via simulation. That's how we'll do it. But this, we'll start out though with first and second order systems and do it analytically. That's what the next lecture is about. So let's switch over to that. Any other questions before
How do these points on this map relate to, I don't know, the time constant of a system?
Yeah, okay. So I just drew, this blue line is just some system response. I mean, it looks like it's probably a second order system. I think it was, I can't remember. I simulated it last year, so I think it's a second order system. So this is let's say it's second order. It's underdamped, right? Because it has oscillation, but it goes to 0, right? It damps out. So the time constant you could associate with it, which is not typically done for a second order system, but you could talk about a time constant, which is the exponential envelope. Whoop, almost had it. Exponential envelope that this damped oscillation follows. Right? The damping ratio is going to govern how much overshoot you have, right? So this, I don't know, looks like to me somewhere in the like maybe 0.3 damping ratio, something like that, but I'd have to go back and look at some examples to be sure, but something like that. It's underdamped, it's definitely not, it has a couple oscillations, so it's not like 0.8 or 0.9 damping, it's lower than that, it could be 0.5 to 0.2. And then the natural frequency, you could approximate the natural frequency if you wanted to by looking at the oscillation peaks here. It's not perfect, but it's one way to estimate what it is. So look at the difference there in time and take 2 pi and divide it by that time, and you'd have approximately the natural frequency. Does that make sense? Okay. Cool. So we're looking at a system that probably has a complex conjugate pair of poles that are stable, so they're in the left half plane, right? And have negative real parts. And there may or may not be a zero in there. It's kind of hard to tell from the step response. We could talk about non-minimum phase systems, but that's a little bit beyond this course. So, yeah. So this was there to demonstrate, though, that even if this was like a fourth order system that was being simulated, we can still define these parameters: the rise time, the settling time, etc.
Sorry, the top slope on this one, what was that?
Oh, this guy right here?
Yes.
I was just drawing the envelope. So whenever you have a damped oscillation, it's damped by this decaying exponential, right? So you have like an e to the minus something t times, say, cosine of omega and t plus some phase. This is the response. So you've got, this is your envelope function, and I'm just trying to drawing that decay. Yeah. All right. So let's go on to the next one.